tell you a story. So I have a friend who lives in Renton, and he introduced me to this person that he knows who used to work as a nuclear submarine engineer.
Okay.
And then he went from
That's a cool guy
the
to know.
Navy to, because he's super duper smart. Like his SAT scores are just like off the charts. And he then went from the nuclear Navy to Hanford as a contractor.
Right.
And I sat down with him and had some wine and, and talked to him about nuclear reactions. And I told him basically what we're doing here at Quantum Kinetics. And I told him the signatures we get the X-ray, we get the gamma, and we get the soft neutron or the thermal neutron. And he took a swig of his wine, put his cup down, and looked me right in the face and said, "That is a nuclear cross-section. You be careful around that." That's what he said.
Yeah.
And that's a nuclear engineer who was on a nuclear sub.
Right, because they know when you're getting real nuclear reactions going on, because they've been dealing with it.
Oh, he's been doing it 20
And
plus
I mean,
years.
you've been verifying this for
Oh yeah.
10 years.
Oh yeah, I've seen the repercussions of it too.
Yeah. So that's the stuff to be careful around. But it's
safe.
also something.
It's safe.
Yeah, it's safe because it's been built in a way to be safe, and it's also operated in a way to be safe.
Yes.
And
right now we're not even operating it at all. Like whenever we do an operation now that we've gotten to this level is when we're going to do an actual industry level experiment, like with a partner, that's when we do it. We don't actually do it anymore at all.
We kind of stopped.
Like,
we stopped
why?
experimenting in our own lab because we realized, like, okay, this requires a little bit more stuff going on, and that's part of what we're excited to do when we get funded. We'll be able to build some much more involved shielding apparatus and establish much more involved safety procedures to allow us to push that edge much more as well.
Yeah, that's a good transition into the NRC 10 CFR 30 and 34 regulations for nuclear fusion reactors. That's a great segue.
Yeah, well, that's an interesting one. Is I've been not digging in too hard. I've been reviewing along, and when I went and took a look at Washington State for the fusion industry is working, or the Department of Health for Washington State is doing, from my impression so far, an excellent job of working with fusion companies. They're trying to really enable companies to push the edge of technology while maintaining a very flexible outlook on things and maintain this goal of safety for people.
Do you want to
because that's what's important. And something that a lot of fusion companies, as I understand it so far, are basically registering their devices as
particle
accelerators.
Right.
Yeah.
Okay, so just for the audience, the NRC, which is a Nuclear Regulatory Committee or whatever, they have a regulation for particle accelerators, and the particle accelerators under 10 CFR 30 and 30.4 is that's a particle accelerator regulation. And just recently the IAEA and the NRC have classified nuclear fusion reactors as actually just particle accelerators. Now, the definition of a particle accelerator, for those who don't know, is one, it has to do transmutation, which means a nuclear cross-section of an influence, X-rays, gamma, neutrons.
And I was seeing some definition in there based upon specific energy levels of emissions. I was seeing like one was like mega electron volt plus, and I think in another place I think I saw giga electron volt plus.
We're going to get to that in a second. This is very interesting, actually. And then the second regulation for a particle accelerator, aka a nuclear fusion reactor, is that it accelerates, decelerates charged particles like electrons, protons, and nucleons, which is what we do with particle oscillation as an energy generator, micro excitement.
And that's what you're doing when you compress a hot plasma, even if it doesn't fuse very efficiently.
if it has a low nuclear cross-section of influence, yes. And then there's a third one, which is the amount of energy input to the particle accelerator, which is 1 mega electron volt. That's 1 million volts. And they capped it at 1 million volts originally with the particle accelerator regulation. The reason why...
Oh, it was a cap, okay.
It was around 1 million volts. The reason they don't want you to go above 1 million volts is because if you go above that, you start transmutating other things in the area.
Yeah, just
there's a cross section that grows, right?
Yeah.
And that's the part where it's really interesting, because in 2023, the FIA and Halion wrote a letter to the NRC requesting that they do an amendment to the particle accelerators to increase the mega electron volt input to way further. And they made a change to the handling of the nuclear waste that is created from the fusion reactor.
It sounds like that might have been motivated, purely speculation here, that might have been motivated by a desire to avoid having to come up with a new classification of equipment or device to accommodate what they're building. So they needed a little bit more headroom to keep it as a particle accelerator and avoid more, I guess, bookkeeping or regulatory mess to kind of organize.
Well, I think what happened there, Brighton, was that the engineers said, we're going to make a, inertial confinement or reverse field confinement or whatever the engineers did to make their reactor. They said, these are the parameters.
So, yeah.
And the rules, when they got dropped into the NRC rules, they're like, oh my goodness, our engineer designed correct.
We don't have a classification.
We're actually outside the zone. We better make an amendment.
Yeah.
And I say, if you're not within the classification of a nuclear cross section, I almost said it, cross section.
Crocs section.
My Crocs are so sweaty.
Putting these in sport mode.
But if what they did there was they moved the goalpost a little bit. Like the engineer said, we don't want to change the voltage input. We want to just keep the voltage as it is originally. But we're going to change the rules so that we fit in the cog fits in the wheel, right?
Right.
Instead of trying to change their reactor to be in that rule set.
Right. Interesting. I'm gonna have to go back and read that a little bit more. I wasn't sure. I guess I was thinking they were talking about the energy levels of the radiations that were coming out.
It's the input power.
Okay.
It's how much. It's like when you pull a rubber band back. Like you can pull the rubber band back this much and you let it go. That's going to have a nuclear cross section potential output. For every input, there's an output.
Right. It's like how far are you reaching with this thing before it gets absorbed in the environment?
Right.
So you want to avoid that spreading out too far.
Yeah.
And that's something that we talk about. I think we've talked about that in the past with Skyshine.
Ooh.
Where you can have radiation.
Tell the audience what Skyshine is.
Well, Skyshine is basically where you have an emission event, you radiate, and it goes up into the sky and hits some clouds or
what's
whatever's
radiating
up
first?
there.
What comes off first to cause Skyshine?
I forget the exact radiation.
Neutrons.
Oh, it's specifically fast neutron flux.
Yeah,
so you get fast
neutrons
neutron flux going way out into the environment, up into the sky, and when you hit stuff with neutrons, it can become radioactive also. So you have a lot of secondary and tertiary scattering.
Yep, that's right.
So you hit the air up above your facility with a bunch of fast neutrons, and it re-radiates downward.
Yeah.
As well
X-rays.
as in all other directions, but it sends down X-rays.
Yeah, it shoots neutrons up, and then it hits the air, and the air absorbs it. Right. And then the electrons get compound nucleused, and then they emit X-rays down onto people's heads. And
so you have to shield over the top of your reactor, not just around the sides of it.
There was actually a case, I probably should, there was a friend I knew who worked at an X-ray department for a medical company. Yeah. And one of the operators there that had been there for like 15 years, he got brain cancer. And the shielding didn't have a roof shielding. So they were shooting the patient's X-rays for the stuff they were doing, and the guy was getting freaking Skyshined. Bam! He didn't know it. No one knew.
Yeah.
And then he got brain cancer, and then they did it. They were like, "Oh, we better put shielding." So when you do a nuclear cross-section event, you have to expect renormalization in the entire universe. You have to account for that.
Yeah. These radiations have the potential to reach out not just in a straight line fashion in all directions. You can't just shield it against one direction and think you're fine. There's a lot of stuff that can happen outside of a facility where you're running nuclear tests.
Nuclear fission, nuclear fusion, you know, and that's where we're really excited about our technology here at Quantum Kinetics, is because we're using safe nuclear processes. And by the way, Brighton, we just got the trademark from the United States Patent Office granted to us for safe nuclear. So that's, I mean, like, cheers, buddy.
Fantastic.
Like that's so great.
Another one.